So hash tables can handle overflow using chain. So in theoretically, you will not experience any occurrences of overflow because there will be always a spot. You create a memory spaces for the new elements if it's necessary. Each bucket keeps a chain of all pairs for which it is a home bucket. Okay, good, good. But I also remind you there will be one small problems or one small things to verify after you build a table like this. Like in a way of checking whether your hash function is working correctly or not. If your hash function is crappy, always give the same buckets, all of these elements, for example, will be up here, right? And you will not receive any of the error messages and you will not notice unless you take a look at the entire list first. So those cases you might need to check. So you can find out if there's anything wrong with the hash functions. So there is some but small risk of using this way. So if I need a hash tables, I sometimes just do it this way, just because I don't want to deal with the error cases. I mean, my data set usually is small enough to handle a linear way too. So that's my stuff, but I don't recommend you to do it. Be careful when you do all this. The chain may or may not be sorted by a key. In this example, I think it's a sorted 11, 33, 55, 66, 36, 69 sorted. If you want, you can do this. Every time you do a inserting element, you do a sorting after that, or you don't have to do it. If it's nicely designed, hopefully you just have a maybe maximum of 1 or 2 elements in each home bucket. And these elements will be evenly distributed in other pointers as well. That might be fulfill the general purpose of the hash table in the first place. So see program 10.20 for hash chain method. But if you take a look at it, it's a simple pointer operation, just adding another pointer. Just checking the home bucket. If the pointer in the home bucket is empty, insert. If it's not empty, go to the end of that pointer, insert. Something like that. Or at the beginning of the pointer, insert. That is, it's a simple pointer operation. So not many things will change from previous code in the linear hashing, for example. Any questions so far? Since you guys told me I speak a bit fast for the last 20 minutes. I don't think there will be ever a question, even if I speak fast, slow. Only time you guys respond is, okay, today is over. And you go, it's like a high school. So hash table with the sorted chain. I like this hash table better than the previous one, but because it has a bit of less elements. This one, I don't like it. Hopefully I can put this last one in somewhere in the empty buckets. It might be better. That's what I mean by evenly distributed. Ideally, single elements for every bucket. That's ideal situations. But we do this just in case buffer overflow, in order to avoid the buffer overflow case in inserting hash tables. So put in pairs whose key is 6, 12, blah, blah, blah. This way, home bucket is key modular 17. That's our hash functions. Then this is the way of doing it. Let's just do 1. 6 modular 17 is 6. So 6 modular 17 is 6. Add 6. 12 is what? 12 is also 12. Add 12. 아이고, 한참 가야 되겠네. 34. Wait. 34 modular 17 is what? 0. So I add the 34. 0 comes because later when 0 comes, they change the pointer and insert this in the front of the 17. Okay? if I was the guy who is implementing this, I'd probably just put 0 at the back of the 34, which way is just fine. I mean, it says so may or may not be sorted, right? So whatever you want to do, it's completely okay with me. So you get the idea of how to adjust the overlapping ones in the table, right? Right, hopefully. Small exercise. Suppose that we are hashing integer with the 7-bucket hash table using hash function fk k modular 7. Show the hash table of 1, 8, 23, 40, 51, 69, 70 are inserted using linear open hashing addressing to resolve a collision, to avoid a collision. Not avoiding a collision. Yeah. So B, repeat part A using chain, resolve a collisions, assuming the chain is sorted. So 2 examples, I don't need to do this, right? It's pretty much obvious. Just big table, 0, 1, 2, 3, 4, 5, 6. And then one of a modular 7 is just 1. Put the location in. If you want to do in chain ways, likewise I explained it. Anyways, you will have your assignment just doing a very simple assignment on this. So 이거 안 해도 되지? 뭐 할 필요 없잖아 이거. 똑같은 건데. 모듈로 하는 건데 뭐 어려울 게 뭐가 있겠어요. 그지? 안 해도 되지? 오케이. 해? 아 이거 뭘 해? 유치원에서 하는 거예요. 유치원에서. So you can I guess this is chapter 10. You can look at over chapter 10. But for this chapter, I think I explained good enough. I mean, if you're really, really tired, then you may not have to read the textbook. I mean, textbook just repeat what I said for the last over 2 classes. So that's up to you. But you will definitely look at the textbook when the assignment comes out anyways. So when is our next assignment due? I forgot. 언제야? 내일 모레? 내일 모레? So I'm guessing you guys already done the assignment 3. 그죠? 다 했겠네. 내일 모레? 내일 모레? 내일 모레가 며칠이야? 수요일. 오케이. 오, 그러면 I think we have to do assignment 5 as well this time. I will give you, yeah. Initially, I was thinking the assignment, total of 4 assignments, but I will give you another assignment through the end of November, probably. 아니요, 되게 짧아요. It's only a very few questions. It's not too much. Okay, so that is it for hashing. It's somewhat very practical. When you actually do the programming, it's very practical, very useful way of doing stuff, hashing. I mean, linear list, linked list. Other than the assignment, you might not encounter situations that you need them. But hash table, quite often, you would need to understand how to use those stuff. So we can continue on the next part. At this point, I think I'm skipping one of the chapters. Maybe after this chapter, I'm skipping one, and I go to the next one. I might come back to the chapter that I skipped or not. That just depends on how much time we will have left towards the end of the course. So, okay. So next one comes something called binary trees. But we all know what trees are from your previous courses. Even you know binary, you know what it means. Simple operation. Some of the stuff that you have already seen it before. Assignment looking quite similar to your previous experiences. But let's take a look at and therefore a bit of formal definitions of this binary tree. Where do they use this stuff? 아이고 뭐가? Linear list. How many times we have seen this definition so far? I think every single chapter has this. because we're still dealing with the list. I mean, in some way or another, especially when we start discussing on how to implement the whatever data structure we discussed, we try to store that information using a linear list. That was a typical case. So every single time it comes, E1, E2, just a series of numbers, if you want to say it, days of the week, month of the year, student in class, or anything that you would like to have it. So it's a serial order 1, 2, 10, for example. If you want to call it from left to right, that's also fine with me too. But trees are hierarchical. What is hierarchical? Well, I mean, whenever you heard the word hierarchical, they usually start drawing graph from top to bottom, right? They usually draw it this way. And there seems to be some relationship between the elements when you go up or when you go down. So it's a bit of structure, order data, hierarchical orders. So there must be some kind of relationship. Upper one is meaningful to some ways to the lower ones and vice versa. Things like Joe's descendants is someone's kids, someone's parents. Corporate structures. Well, usually you draw, universities, they don't draw that, but in your companies that you may be working for later, they usually draw this way, right? CEO, more, vice president, BP1, BP2, BP3, blah, blah, blah. And then under here, there is a small department chairs, and you will be bottom somewhere right here. Yeah? That's, I mean, usually undergraduates, when you have a job, that's where you are, and you wanted to go up one by one, right? That's a typical example for hierarchical, organized structures, right? 그럼 여기 어디 있겠어? Me also somewhere down here. 여기 똑같아. 여러분들이 여기면 나라면 여기쯤? It's not so much different from us. Corporate structures, government subdivisions, Ministry of Health, Ministry of Education, it's all part of the government structures out there, right? Software structures. You guys, I don't think you guys have enough experience to write a big programs or reasonable sized programs that requires a certain structures. Maybe it's like something called the modules. This module work with the other modules and stuff like that. If it's that way, then you might need to organize your code in this way, classes and code in this way. So those are the typical examples, and of course, similar examples are discussed in the book 11.1, 11.4. This is one of the examples they give. Joe is the guy. We have seen this similar stuff last time. What are the examples of hierarchical order sets in this way? Maybe Joe is the father and is the kid, blah, blah, blah. You go down that way. We all know how to trace this. 그죠? Definition of tree. Tree is T. It's a finite and non-empty set of elements. Tree T, finite non-empty set of elements, non-empty set of node. So that's a definition of tree. One of these elements called the root. Root, but we all know where the root are. Probably one in the top. Root. The remaining elements, if any, are partitioned into trees, which are called as subtrees of the T. If you look at the tree, if you start dividing the tree, one of the ones that taken out from the one big tree is also a tree. 그죠? It's a tree is combination of other smaller trees. 그죠? 여기서 이만큼 떼어가면 that's also a tree. The part you take it out from the big tree called the subtree. Subtree of the subtree is also a tree. Subtree, subtree, subtree is also a tree. That reminds us one smaller fact that we have looked at so far. If something can be divided into smaller parts, what is a typical way of doing programming for those, handling those elements? Yeah, maybe it's a good idea to use a recursive somewhere in the tree because you're going down smaller, smaller, and then you go back up. Recursive is a very good example on the operating on the tree. Typical assignment questions too. Since we've been looking at many different data structures from beginning of the class, what might be the natural step after they give you the definition of tree? 우리 데이터 스트럭처 많이 봤잖아, 지금까지. 아유. After they give out the overall structure of the tree, then naturally they will probably explain us to what are the implementation ways of doing this? What are the implementation of these trees? Answers always in two ways, array-based and linked list-based. 그죠? 뭐겠어? Linked chain as well. It's obvious, chain, I might able to do this chain right away. I mean, it's not the form of this way anymore, but it's up and down. So, but it's not gonna make too much difference in the tree using chains. And array. In order to store this into an array, we might need to find a way of how to read on elements in this tree. Which way first? Do you want to look at the elements from the top to bottom, left to right? We have to agree upon a certain ways to read this trees. I mean, by extracting elements, which order should we look at each element in the tree? If we agreed upon a certain rules, then we just stored them into a tree in that way, exact same way. So that it might be another approach to think of. So that's actually entire chapter is about. They tell you different ways of storing, implementing these trees. And before that, they start discussing some of the property of a tree. One of the important properties, subtree. Subtrees of tree. If you divide up the tree, that's a subtree. Subtrees of the subtree is also tree as well. 보겠어. Subtree obviously this. If you look at that Joe diagram, Joe's descendant, Joe is a root, the guy on the first. If you look at this, what might be the property of a root? What might be the obvious property of a Joe root? 제일 위에 있는 거. Doesn't have any guys on the top, right? No, it's no descendants of anything. So, root. And if you divide it up, subtrees. This is also a tree. One edge, still a tree. Still a tree. It's a wonderful example for the recursive way of implementation. I still remember my first assignment in a tree. My recursive function didn't work. It never ended. It just stuck somewhere in the tree. I still cannot forget that experience. Stay over 2 nights straight and still cannot figure out how to get it working. I never want to do that again in my life. But this is a tree terminologies for tree. The elements and the top of the hierarchy is a root. We know that now. Joe is the root. Elements next in the hierarchy are children of the root. Descendants, same way, children. Elements to the next in the hierarchy are grandchildren of the root, and so on and so on. Children, grandchildren, grandchildren. We all know what it means. There is one definition at the below. What are the leaves? Elements at the lowest level hierarchy are the leaves, or simple property of the leaves, they don't have any other edges coming out from them. There is no below stuff. So usually one at the very bottom of the tree is called leaf. If has a branch, then no longer a leaf. So leaf and root. Like I explained the tree first time to you guys, if you flip over this tree, then it looks like an actual tree. 그죠? 나무 이렇게 생겼잖아. 입 달리고. If you flip this up, tree. We're still discussing the same stuff. Other definitions. Leaves, parents, grandparents, siblings, ancestors, descendants, it's all the same. We all know what it is. In this examples, leaves are Mike, Al, Sue, Chris. Do I ever ask you this question, such questions in the exam? No. If I start asking you these type of questions, you can kill me. You can kill me. Yeah. 이건 뭐 그냥 하는 거니까. 이거 모르는 말이죠. Parents of Mary is Joe. Of course, Joe is on the top. Grandparents of Sue is Mary. Joe is 2 steps up. Siblings, Mary's siblings is Anne and John, which they call it at a later same level. Level 0, level 1, level 2. If they're in the same level, you can call it as a siblings as well. Ancestors of the Mike. Well, Mike 어디 있어? Where's Mike? Yeah, ancestors of the Mike. Then anything above the Mike will be the ancestors. They don't distinguish grandparents or like that. So if you want to implement this, what can you do? Maybe 2 ways of doing it. If you want to implement this, maybe you implement a tree, for example, linked list way. Okay, the search function, you built a function. Is that function returns the ancestor of the given person. What might be the first step? 2 different approaches, I guess. First thing, search where Micah is. If Micah is in the tree, okay. If Micah is not in the tree, then your function should returning no Mike in the tree. Right. I also said 2 approaches. So why you can modify the search function of that person while you're looking for certain functions, certain trees, certain elements in the tree. Then you have to explore the tree from top to bottom, right? And there might be some successful search at the end. So you just simply report that path that found the mic. In order to find the mic, I could have gone to here, could have gone to here, could have gone to here, right? If I take this path, no mic, no mic. This path, mic. So I just simply report the what node that I went through. And then except mic, I report these 2 ways. That's the first way. Second way, after you found the mic, what might be the choice? You can simply go up until you reach the root. I mean, those are the 2 dumb approaches that you can implement. Right? We can tell by looking at this graph, but if you try to implement this on the program, then it's a slightly different story. You have to define the data structure for this tree. I mean, implementation details of the tree. You have to write a search functions. You have to modify the search functions to report the ancestors of a certain node. So it's involving path search. We're not even discussing for efficiency issues, right? If you start considering the efficiency, which one is faster way of doing it, then another headache is added too. 이거는 이렇게 그림을 보니까 금방금방 나오지. 예를 들어 구현해라 그러면 기본적으로 구현해라 이렇게 지금 얘기한 게 딱 나오게 되죠. 그죠? 그럼 조금 어려울 수도 있지. Descendants of the Mary. Likewise, I start find the Mary first. Go down. Anything that is below Mary, start exploring the trees. Just report them. That will be my answer to this function. So each one you can implement as a function for your data structure, tree data structure. What if I ask you to write a pseudocode for this, or even a small piece of code for this one of these functions in the final exam? Of course, I give you some details on the data structures and some operations that you can use. You should be able to do some of it. Again, I don't looking for any syntax issues, grammars, I don't really care. But pseudocode, I do care. And like to see whether your ways of doing it actually works. So that's one way to practice your programming skills. Without actually typing in, you can do it in your head. Or if you're really, really anxious, then you can certainly type some of the code in your textbook. You could just simply copy it first and then try. Do it. I mean, I keep hearing some of the complaints, not complaints, but yeah, okay, let's complain about some of the programming like assignment. You have your resources right away in your books. They do provide all the source code. So if you wanted to do more, then you are always welcome to do it. Has anyone ever tried to just copy some of the code in your textbook and run it in your computers? 해본 사람? 그 혹시 책에 나와 있는 프로그래밍 예제 이런 거 그대로 한번 복사해서 해본 사람 있어요? 안 시키면 안 하죠, 그죠? 안 시키면 안 하죠. 나중에 회사 가서 돈 주면 그때 하겠지, 그죠? 열심히 해봐라. 그때 가서 고생할 거 지금 고생하는 게 훨씬 나아요. 그러니까 한 번씩 시간 날 때, 뭐 학기 중에 너무 바쁘면 방학 때라도 한 번씩 해보면 도움이 될 거예요. So that is other smaller definitions and some of the possible applications on this in the actual implementations stuff. So levels and heights. Root is at the level 1. Its children is at the level 2. 1, 2, 3. Okay, I'm sorry. It's called at level 1. Height, depth, and number of levels. Height is also height of the tree, also referring to how tall is the tree. Same as what's the maximum depth of the tree, how much that you have to go down. That is the same thing. That is also equal to the number of levels of the trees, right? So root is level 1, Joe is level 1. So the level 1, level 2. Wow, this is actual kindergarten stuff. 진짜 유치원에서 가르치는 것 같다. Level 4. What's the depth of what's the height of this tree? 4. What about a no degree? Just a small definitions to interpret the trees. No degrees. Definition of no degree is a number of children it has. Number of children it has. Or later when we start discussing some graphs, then this is my node. How many lines actually coming in and out of this node? I have maybe 3. That is a no degree of this node is 3. Likewise, this way. No degree is the number of children it has. Joe has 3 branches, so no degree of Joe is 3. Anne has 2 children, 2, Mary 1. Obviously, Leaf has 0. So if you keep track of this no degree, you might be able to find a leaf node just looking at the no degree in the structures too, right? If you know just look at the no degree, you can find out the leaf stuff. I mean, without exploring the entire tree from top to bottom. Tree degree is what? They call it as a maximum node degree. So among all the node degree of a tree, you get the largest value of it, max. Node 1, node 2, node 3. In this tree, the maximum node degree is what? 보자. Yeah, 3. Because Joe has 3, the others are smaller. Good. Binary trees. We all know what binary tree is. What is a binary tree then? name speaks itself, binary tree. 뭐야 binary tree? Probably node with a maximum of 2 node degree. Only 2 branches from a single node, max. 1 is okay, 2 is okay, 3, no. If you start talking in 3 branches, that is no longer a binary tree. It's also good for what kind of, it's also, you can think of like yes, no tree. If you go left, yes. If you go right, no. Continue on that way until you try to find an answer for that, whatever question that you are asking. So, definition, a finite collection of the elements. Well, it says possibly empty. Possibly empty. But if you remember the definition of a tree, they say non-empty tree. So there is a difference here, non-empty tree. But in binary tree, it can be empty tree too. A non-empty binary tree has a root element, and the remaining elements, if any, are partitioned into a 2 binary trees. Same way, we're referring to a subtree. And this time, any subtree in the binary tree will be also a binary tree. So it's binary tree. So this to give you a bit of more twisted way of definition, but it's more of a formal way of doing it. Let me read it again. A non-empty binary tree has a root elements. The remaining elements, if any, because they could be, if any, are partitioned into 2 binary trees. Call it as a left and right subtrees of the binary tree. Also, that sub-binary tree will have a left, right, left, right, left, right. What might be the worst case binary tree? Yeah, we discussed this too, right? One way. If so, what might be the depth of this tree? Assuming there's n elements. 그러면 depth가 어떻게 되지? n-1인가? n인가? n이구나. n. 그죠? 뭐냐면 그냥 쭉 이렇게 서 있잖아. 그러면 depth 1, 2, 3, 4, 5, 6, n. Also binary tree. Left side is empty, this side is empty. So these type of properties later are given a 증명 proof in your textbook as well. 근데 뭐 증명할 게 뭐 있어? This is the proof. Now are called a left and right subtree of a binary tree. This way, difference between tree and binary tree. A binary tree may be empty. Tree cannot be empty. No node in a binary tree may have a degree more than 2. Like I say, only 2 branches. Yes or no? Yes or no? There's no medium in it. Whereas there's no limit on the degree of the node in the tree. Trees, still tree. Binary tree, only 2. No limitations on the degree of the node in a tree. Subtrees of a binary tree are ordered. Those of the tree is not ordered. So if you are building a binary tree, the elements will be in order. Trees doesn't require that ordered elements in the content of the tree. Different when viewed at the binary tree, same as when viewed at the tree. These two, both are tree, but if we're taking this definition as ordered tree, hopefully ABC in order way, I look at it as a binary tree. ACB, unless I have a special ordering rules, that's not a binary tree, but a tree. Binary tree expressions. We did discuss similar stuff when we discussing compilers, some ideas for compilers. Those of you who take the introduction to computer science, I think So binary tree expressions. This is in order. So A times B, C divided D, plus in the middle, that's one way. Or A, B, C add, D add. It's kind of obvious. But there's always a rule to how to read. We agreed upon how to read this tree and plus express this expression at the end. So if you look at this closely, this is giving you a hint on how to store this tree in a list. In a list. Ooh, if it's a list, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I store this tree. Okay. These are the binary tree property, 3 binary tree properties that discuss in the textbook, our textbook. A drawing of every binary tree with an n elements n is greater than 0 has exactly n-1 edges. Okay, so every tree with an n elements, total number of lines will be n-1. So just looking at this example, how many edges between there? If there's n elements, n-1 edges. I mean, even if you look at the proof, they do it this way. It's quite obvious. A binary tree of the height h, height is greater than equal to 0, at least h, and most 2 to the h minus 1 elements. 이건 뭐야? A binary tree of height h, h is greater than 0, at least h, or at most 2 to the h minus 1 elements. 저건 뭐야? What does that mean? How do you draw that in order to prove that? Well, let's draw case by case. If you can cover all the cases, then okay. It says tree with the height h. Height h, let's say height is 2 or 3, 2. At least 2 elements, right? I don't have this. Without this, I still achieve a height of 2, right? At most 3. 2 to the 2 minus 1. 3. 뻔한 얘기잖아. What if we're looking for 3? Still 1, 2, 3. The minimum element, the minimum number of elements in this tree is 3. I still can have height 3 tree. But total number of elements that I can have, the maximum it will be how many? So 2 to the 3 minus 1, or 7. 1, 2, 3, 4, 5, 6, 7. Or I might not have this. 1, 2, 3, 4, 5. So elements will be between h and 2 to the n minus 1. This is somewhere in n. See, it's proof on page 427. They do this way. It's a proof. It's a proof too. I mean, they write more nicely, but that's a proof. So this is binary tree properties. So you can use this proof. You can use these properties to maybe prove something is not a binary tree. Maybe. If you're given a tree that this property doesn't apply, perhaps those are not the binary tree. Another way of verifying whether things are binary or not. It's quite obvious properties, right? They just make it fancy writing that way. 그죠? third one is also quite obvious as well. 아이고 여기 그려놨구나. 정신이 나갔습니다. Height of a binary tree, the third property, height of a binary tree that contains an element, n elements, and is greater than or equal to 0, then is at least log n plus 1 and at most n. At most n. Log n plus 1 is log of n or at most n. Why do they say at most n? N elements, height of a tree is at most n. At most n, or if we do this, it's a log of n, right? It's 8 elements, 2 to 3. Log 2 of 8 is 3. 그지? 아니야? 아이고 갑자기 나 로그 까먹. log of 3, what? 3. They just add plus 1 just to make sure if it's a 7. They try to make it close to 3. They want to have a values. Obvious, right? So height would be between this and this height number. So this is also property. Again, if you look at the proof on 427, they also try to explain these figures in the words. So quite obvious of doing it. 이거 뭐 뻔하잖아, log of n. What if you're working with maybe ternary tree? Maybe tree has 3, maximum of tree 3. 이렇게 하면 the height of this tree, if there's an n elements, what do? Maybe, I don't know. 이건 안 되겠구나. 이렇게 하면 안 되겠구나. 이렇게 해도 되나? log of 3 of n 이렇게 해도 비슷하게 나오긴 하겠다. 그죠? 몰라, 찾아봐. Anyway, those are the 3. It might not be correct, but I mean, because I haven't seen any ternary tree examples, there might be some odd cases that doesn't apply. So don't forget about this. But binary tree is the way. 3 properties to discuss in binary tree. Will I be asking any of these proof questions? Maybe. I just wanted to know whether you read the textbook or not. But even if without reading the textbook, you all know how to prove that using these simple examples. I mean, these examples cover every single case. So proof, done. It's quite obvious properties, right? 이거는 뭐 크게 어렵지 않죠? 근데 막상 proof 증명하라 이렇게 적어놓으면 벙찌죠. 그죠? property 주고 증명하라. Last midterms. I don't think how many times I said to memorize. If you don't understand it, memorize those big O definitions. Surprisingly, at least 30% of you didn't write the question right. I was very strict on that question. 한자로 틀면 부분 점수 안 주려고 그랬어. 하도 많이 얘기를 해서. There was a lot of variations, but I try to give the full mark. But some people didn't even write it, and they write a definition that I'd ever seen before. So 그렇게 외우라고 해도 안 외운 사람이 20-30%가 있다는 사실에 상당히 놀랐습니다. 내가 얘기했지. 그거 안 쓴 사람들은 내가 나중에 리스트 여기다 실명을 내가 공개하겠다고. 진짜 그럴지도 몰라. 그 문제만. 점수는 되도록이면 다음 주 중에 알려줄게. I probably sometime next week, just like other classes, I will usually post on your midterm marks, averages and max and minim. Because someone asking me are you not revealing the midterm grade? I do. 그런 사람들이 몇 명 있더라고. 잘 모르는. 원래 중간고사 점수 안 알려주세요 물어본 사람도 있는데 나 안 알려주지 않죠? 알려주죠? 네, 다음 주 중에 꼭 알려줄게요. Also, you will have your time to visit my office if you want to verify your papers, then we will set up a time that you can come check your papers too. Okay, so next one, 3 properties, and I told you to read this proof in your textbook too. So next one, a full binary tree. They start adding an extra features into the simple binary tree and giving a slight different slight different variations of other trees. Full binary tree of a height h has exactly 2 to the h minus 1 node. Everything is full. Everything is full. There's no spot left for extra elements. That's why you can have 2 to the h minus 1 elements. Numbering the node in a full binary tree. So I'm going to give them a number, each node. Maybe 1 through n, right? Oh no, 2 to the n minus 2 to the h minus 1. Yeah, n node. So number by levels from top to bottom. Level 1, I'm going to do this way. I could make a rule that I could do backward, right? 1, 2, 3, 4, but I'm going to do this way. This is full binary definitions, full binary tree definitions. Within the level, number from left to right. Level 1, only one element, 1. Level 2, okay, I'm in my level 2. It says number left to right. Left to right, 2, 3. Level 3, 4, 5, 6, 7. So if I do that numbering, you're making a full binary tree. No number in full binary tree. That's what you have. If I miss an element in somewhere, then it will not be a full binary tree because the definition says has to have a 2 to the h minus 1 node. It has to be a full tree. Parents node, node number property of a full binary tree. Parents node I is a node I divided by 2 floor unless I is 1. Parents node of I is node n minus 2. Node 1 is root, has no parents. Parents node of I is 2. I is 2. In this case, divide by 2, it's 1. That's my parents node number. 3 divided by 2 is what? 1.5. I take the floor. 뭐야, 버리고 0.5, 1. You can always find the parents node in that parents node number in that way, right? Because this is full tree, you can always do that. Obviously, node 1 has no parents. I don't have to mention that. Node number property of a full binary tree. Left child of node I is node 2i unless 2i is greater than n when is total number of node. If 2i is greater than n, node I has no left child. Simply means I'd like to find the node number of my left child. 2, I is 2 here, 2 times 2, 4. 4 times 2, 8. So, obviously. But they just do have one extra conditions that if that 2 times I is greater than total number of elements, then it's not right. They just do a checking condition on that part, unless 2i is greater than n. If not, 2i is greater than n. 그러니까 2i가 전체 숫자보다 작을 때 you can always explore the node number of your left child. So, obviously, what is a node number for right child in this case? 뻔하지, 숫자 노름도 아니고 2i plus 1. So, quite obvious. Likewise, they do an extra checking condition that 2i plus 1 should be less than the total number of elements in the tree. Just the extra checking conditions right there. If 2i plus 1 is greater than n, node I has no right child. Cannot have more than what I have. So no left child, no right child if the number exceed. That's a very simple properties. 그만하자. Complete binary tree with the end node. 여기까지만 할까? No, I will come back to this on Wednesday. I'm gonna call out the attendance now. Any questions for today? Hashing binary tree, very easy binary tree definitions. 질문.